Hello everyone, welcome back to the Organic Chemistry course. In the previous videos, we have discussed the scope of organic chemistry, its applications in industry and everyday life, IUPAC nomenclature of alkanes, the functional groups, and much more. Today's video is an introduction to stereochemistry, one of the broadest and most important subjects in organic chemistry. We will begin with the definition of stereochemistry. Then, we will discuss the different styles of representing molecules in 3D, for instance, space-filling models and CPK models. Finally, we will evaluate 4 ways of depicting a molecule in 2D without losing much information about its real geometry. Let's go! Before starting the lecture, it is crucial to define the concept of stereochemistry. Stereochemistry is a part of chemistry devoted to the study of the spatial structure of molecules and the effect of this structure on the physical and chemical properties of substances, on the direction and speed of their reactions. Stereochemical approaches also help us in solving problems of theoretical organic and inorganic chemistry. A well-known example from this field is the use of the results of studying the asymmetric synthesis of the optically active substances. The relevance of this complex and interesting branch of chemistry was proved last year by outstanding scientists Benjamin List and David Macmillan. They were awarded the Nobel Prize in Chemistry 2021 for their development of organic catalysis, which is an accurate new tool for molecular construction. This had a great impact on pharmaceutical research and has made chemistry greener. Catalysts are thus fundamental tools for chemists, but researchers long believed that there were just 2 types of catalysts available, metals and enzymes. Benjamin List and David Macmillan were awarded the Nobel Prize in Chemistry 2021 because in 2000s they independently developed the 3rd type of catalysis. It is called asymmetric organic catalysis, and it is based on the usage of comparatively small organic molecules. Here you can see several examples of the molecules which are used as catalysts nowadays. It is obvious that when dealing with stereochemistry, it is necessary to visualize the spatial structure of molecules. For this purpose, chemists have developed different types of stereochemical models. All of them are to some extent useful, but each of these models has its limitations and weak points. We choose the specific model depending on the nature of the problem that should be solved. So let's evaluate the advantages and disadvantages of the most popular models for displaying the spatial structure of compounds. The most correct representation is given by the Stuart-Brigleb models, which are often also called space-filling models. The figure shows carbon and hydrogen atoms in the form of spheres of different diameters. The sizes of the spheres to some extent characterize their van der Waals radii. In this model, the distances between the centers of the balls correctly represent the length of the bond as a sum of covalent radii. In addition to the correct information about the length of the chemical bond, space-filling models showed that the atoms in the molecule are packed tightly. It means that the part of the space into which an external, to be more precise, chemically unbound atom cannot enter is shielded by spheres. However, this packing does not always allow you to get a picture of the mutual arrangement of the nuclei of atoms in the molecule. To get rid of this disappointing feature of the Stuart-Brigleb model, the so-called ball and stick model has been developed. In contrast, it correctly represents the length and the direction of the bond, but creates a false impression that the molecule is empty. In other words, it seems that there is a lot of empty space between the atoms, which is not true. So, the main drawback of the ball and stick model is that it doesn't create a picture of filling the internuclear space with the electron density. It seems that it's virtually impossible to simultaneously depict the space filling and the bond length correctly. Now on the slide you can see 3 molecules that are depicted using a ball and stick model. Finally, the Drading models, just like the ball and stick model, correctly show the bond length as well as accurately depict the valence angles between them. However, the nuclei of the atoms in them are denoted not by the balls as before, but by the points and the rods representing the bonds. This model has the same disadvantage as the ball and stick model. Therefore, in order not to create a false impression about the emptiness of molecules, we should get used to the idea that the balls in the ball and stick models and the nodes in the Drading models represent only the nuclei of atoms and not their total volume. Here on the slide you can see a table summarizing everything said before. Don't hesitate to pause the video and inspect this table carefully. If something isn't clear, you know where the comments are. To sum up, all models have their pros and cons. It is impossible to single out only one model for all occasions, but you need to understand that each model serves different purposes. We got acquainted with the various types of models that reflect the spatial structure of a molecule in space, but how to convey the spatial structure of a molecule on a flat sheet of paper? Well, to solve this problem, chemists have come up with several ways that allow them to display the spatial structure of a compound on paper just using a pencil. Different types of conventional stereochemical formulas, shown in the figure, are used to reflect the spatial structure on the plane. You may ask a completely logical question: why not use the three-dimensional models that we considered earlier? The answer to this question is simple: these models can be used. However, using them is impractical and inconvenient, since each atom will have to be represented as a sphere that connects to another sphere, etc., and it is quite time-consuming. So to create the 3D models, we need to use special software, which is not always accessible. Now on the slide you can see 4 most popular ways to illustrate molecules in 2D while solving stereochemical tasks. Let's go through them one by one. We will start with the Wedge-Dash Diagrams. Wedge-Dash Diagram is a self-sufficient way of displaying the structure of a molecule in space. For the correct representation of such diagrams on paper, you need to remember that the sp3 hybridized carbon atom has a tetrahedral motif, which we have already discussed in detail in the previous lectures. To draw such a wedge-dash diagram, you need to place 2 bonds coming from the carbon in the plane, and the other 2 respectively behind the plane and in front of the plane. Let's figure out how to draw wedge-dash diagrams and use the compounds mentioned earlier. To begin with, we need to select those bonds that will line the plane of the paper. For convenience, we'll highlight them in red. Next, we select the bonds in such a way that one bond is located behind the plane and the other one is in front of it. I suggest you pause the video and take your time to take a closer look at the figures on the slide. Once again, the red parts of the molecules lie in the plane of the screen. The dashed bond is pointing from us and is located behind the plane, whereas the solid wedge indicates that this part is pointing to us and is located above the plane. So the methyl group in 2-methylbutane is pointing to us, and the hydroxyl group OH is cyclopentanol is located behind the plane of the screen. I hope now it is clear for you, and if not, don't hesitate to ask your question in the comments to this video or in the specific thread on our forum. Let's move on to the next quite intuitive representation of 3D molecules on the plane. The so-called Sawhorse diagrams are similar to the Wedge-Dash diagrams. They're used to depict 2 carbon fragments of molecules. The main advantage of these diagrams is that they graphically depict the arrangement of substituents of carbon atoms, but the disadvantage of such diagrams is that they are inconvenient or not at all suitable for large molecules. For instance, the picture of butane has been drawn in such a way as we were looking at the molecule from the top right corner. For a better understanding of this representation, we have translated similar molecules from Wedge-Dash diagrams to Sawhorse diagrams. And here you can see the animation of how we can obtain the Sawhorse diagram and how the molecules are depicted in this mode. I guess now we're ready to move to the next popular representation, namely Newmann projections. The Newmann projections are constructed by looking at the image of a molecule along any CC bond. The nearest carbon atom to us is denoted by a point, and the distant one by a circle. The other bonds are depicted by solid lines at an angle of 120 degrees. Newmann's projection illustrates the dihedral angle between the various substituents. It is important to note that no matter which side we look at the molecule, in any case, Newmann's projection will be correct. And here you can see the animation of how we can obtain the Newmann projection, starting from the previously discussed Sawhorse diagram. I strongly recommend you get used to Newmann projections, as they are very common in organic chemistry, and we'll use them quite often throughout the videos. Let's discuss the last projection that is important for us now. Fischer's projections are named after Emil Fischer, who suggested using them back in 1891 for carbohydrates. However, projections can be used for other organic compounds classes as well. Let's see how to apply the Fischer projection to lactic acid on the right hand side. For the transition from the model of lactic acid to Fischer's projection, it is necessary to orient the tetrahedral carbon in such a way that the horizontal pair of bonds are directed towards the observer and the vertical pair points away from them. Now on the slide you can see the wedge-dash diagrams of L-alanine and 2,3-dihydroxybutanol, whereas on the right hand side the corresponding Fischer projections. Well done! We have briefly discussed the most projections. Here you can see several molecules depicted with all the mentioned methods. Now it is your turn to take over. Try to redraw these molecules. Pause the video and take your time. Done? Here are the right answers, check yourself. Well, that's it for today. Let's quickly revise all the things we learned. We have begun with the definition of stereochemistry. Then, we have moved to the different styles of representing molecules in 3D, for instance, space filling models and CPK models, and Drading models. Finally, we have evaluated 4 ways of depicting a molecule in 2D without losing much information about its real geometry. In the next video, we will learn several important rules about Fischer projections and how to transform the Newmann projections to Fischer projections. We will also solve several exercises on this topic and have an interesting outlook to the importance of stereochemistry in drug synthesis. If you have any questions related to this topic or any other topic in chemistry, biochemistry, or pharmaceutical sciences, you are more than welcome to ask them on our website and forum or in the comments below this video. We'll be glad if you give us a like and subscribe to our channel. Thank you very much for your attention and we'll meet once again in the next video.